That's how the of course, so property value is bound, that's like a secret.
Yeah.
Like that was the.
Oh, yeah. I can.
Yeah, you live with each other. Yeah. It's a really nice schematic.
Yeah.
Okay, so it is 9:30 and we're going to continue this topic of combinational components. And one of the combinational components that we're going to cover today are ALUs. On Wednesday, I will help you guys with the lab and go over the lab. But again, please look at the lab before you come to both lecture and the lab so that we can be more effective with our time together and you can be more successful during the lab time that you have. Okay, so first things first, review from last week. So MUX as general purpose logic. I want you guys to work on doing this. So you want to map the equation ABC is equal to this Boolean logic equation to using this 4-to-1 MUX. And I am going to constrain you so that we all have the same answer. The most significant bit of selector is, oh, I don't have N enabled, is A, this is B. So do work on this, and there's no like multiple choice answer here. So when you are done working on this, just answer to the poll anything. And I'm trying to pull up the poll. Is it going over there? Yes, that is why I can't see it. So what is this? So we're lecture 9. Okay. Yeah, it's active. So it's 391 today. So answer anything to the poll once you are done individually on this. Okay, and do just complete the circuit. Done. There are still 8 people working on this.
People?
391. The 4 is still underway. I think that's sufficiently enough where we should go over this together now. All right. So, first step in this, what am I going to do? Yeah, so first one I should check to do is 0, 0, right? So let's fix A and B to be 0, 0. So if there's 0, 0, what happens to my equation? First term is, second term is, third term is. So this simplifies to, and then 0, 1. So
I got confused. Where does the C come from?
oh, because so if I fix, oh, it's easier for me to point. So A is 0, right?
Right.
So no matter what B is,
C.
this is 0.
Right.
A is 0, so no matter what C is, this is 0.
This is
B is 0, but it's inverted. So B invert is 1. So 1 and C
C.
just become C.
Just one C. So we
And then-
choose C because in the first part, it's just A and not B. Then this doesn't include C.
Yeah, so we just simplify each one of these individually. And then we have 0 or 0 or C. So 0 or anything just becomes that one thing.
I understand now. Thank you.
All right, so now we have 0, 1. So first term is again, second term is, and then, so this is 0. And then 1, 0. First term becomes, yeah. And then, yeah, I was looking at the second term. I was like, wait. And then I don't have to check anything else, right? Because 1 or anything is just going to be 1, right? And then 1, 1. No, we just have C naught. Are we good with this? Okay, so next thing that we are going to talk about is ALU. So ALU stands for arithmetic logic units. And we saw a small example of this already before, but you have these two inputs, X and Y, and based on the operational code, you're going to output a different function between X and Y. Like the operation code can say add X and Y together, multiply x and y together, subtract x by y, things like this. So before we go into how to make this ALU, we should first look at how to multiply in binary. And just like how we add the same way that we add in decimal that we learned in grade school, multiplying is no different. So multiplying these positive or unsigned binary numbers is exactly how you would do it in grade school. You take the first one, multiply it by all of the digits in the top one, and then you get this result, right? And we just repeat that for the next digits until we get through all of the digits. And multiplication in binary, oh, the other thing is it's important to shift left by 1, right? Because this was for the ones place, this is for 2 to the 1, this is 2 to the 2, 2 to the 3, right? And multiplying in binary is pretty simple because you only have 2 digits, right? It's either 0 or 1. So when you multiply, your result is either 0 or 1, right? And because of that, all of these individual results can be simplified to just AND gates, right? You're only going to get a 1 if they're both 1. Otherwise, there's a 0 somewhere, so the result would be 0. So in terms of how this looks like in hardware, it's a bunch of AND gates, and then you have circuits that are going to add the results together. So here we have A, right, along the top, and then B is our multiplier. So we're going to multiply A by B. And what you can see from these connections with B0, so this is B0 times A3 times A2, A1, A0, right? And the results from these gates are going to the lower bits because they are the rightmost ones. It's these results. And then for B1 times A, so again, these 4 results, we're shifting them to the left by 1 by adding this 0 here. We see this? So that's how we do this line. And then we add those numbers together. It gives us our intermediate result as the lower bits down here. Then we again have B2. And B2 we have to shift by 2 because that corresponds down here, right? And again, we do our add, and then we have those corresponding bits. B3 result, we shift by 3. And then we get our final number down here. We see this? Okay. So I would not ask you to make this. I just want you to be able to read this and understand this. Okay? All right. So division is a little bit more complicated, but just like addition, I mean, multiplication is just addition many times over, right? Division is just subtraction many times over. How many times do I need to subtract this number by this number is my quotient, right? And then you would have some remainder. So it's not as simple in hardware, like how we can just turn everything into AND gates for the multiplication. And to do division, we actually have to do this subtraction. There is a more efficient way to do this, but I'm not going to cover it in this course. If you are curious about that, I do have slides and we can talk about it outside of the course. But really, all that you have to do is set the quotient to 0 first, and then we're going to subtract the divisor from the dividend. And we'll check if the dividend became negative or not, because if it did, then our divisor was larger, right? And if it did not, then we add 1 to the quotient, right? I subtracted 1 of this so far, and if the dividend is still less than the divisor, then what? No. If the dividend is still greater than the divisor, then we subtract another one, and we add 1 more to the quotient. So now I've subtracted 2 times this number from the dividend, and I keep doing that until the dividend is finally less than, once the dividend is less than the divisor, then I cannot subtract any more of it, right? So my quotient is the result, and then I also have the remainder, which is the rest of the dividend. Whatever was left over that couldn't be subtracted, because now my divisor is too large, right? So here's our example. We have, this is 5, this is 2, right? First step, subtract 2 from 5, right? I get 3, and I add 1 to the quotient, because I wasn't too large yet. Subtract 2 from 3, I get 1. Again, I add 1, but now 2 is larger than 1, so I'm done, right? So my quotient is 2, my remainder is 1. Right? So 5 divided by 2, the quotient is 2, remainder is 1, right? So we can check our work. We follow this? Makes sense? Alive? Tired? Monday? All right. So going back to the ALU, remember we want to be able to do these multiple different functions operating on the 2 operands based on what we're going to call ALU op, or the ALU operation code. And the main thing that we want to concern ourselves with is the result, but you also have these other flags potentially. Was the result 0? Is there overflow? And for addition and subtraction, maybe you need the carry out for some reason, right? So here we're going to have an ALU, and if the control says 0, we'll do AND, 1 is OR, 2 is add, and then 6 is subtract, 7 is 7 less than. Right, so that's just like a basic, if the ALU is just a box, right? So how are we going to build this ALU? And we're not going to build that specific one, but how are we going to build a ALU? We'll start with this very simple one. We want one that can perform AND or an AND. That's all we wanted to do for now. So we're going to first create the Boolean logic equations or blocks that implements the and or the add, right? So here's our and, here's our or, here's the add between the two inputs. And then in order to select which one is the right operation, we have a mux at the end. So in these ALU blocks, all three of these operations always occur. It's just that you select one as the end result. So even though you select that you want the operation of an add, you still consume the energy to also do the and the or. But do we see this? And how the mux is selecting? So if I select 0, what is my result? And if I select 1, select 2. Yes. So then to extend this beyond 1 bit, because this is just 1 bit, right? 1 bit is not very useful most of the time. We want more. So if we wanted to extend this, what we would need to do is take that small function block, copy and paste it, say 32 times, right? So if you were to do this in something like VHDL, you would use, say, structural modeling, right? You can design this in maybe behavioral, data flow, however you want, but then to make this, you would do structural. So you're going to instantiate, this one is for the least significant bit. This one's for the most significant bit. And in terms of the and or operation, it's very simple. There's no need to connect the ALUs in between each other. But in order to do the add operation, we're doing this triple carry. The carry out goes into the carry in. Right? So just like you guys did with the previous lab. You can do anything. You could do it behavioral, you could do it data flow. You could do it structural. I wouldn't do it structural. It's too simple. Doesn't make sense to do it structural, in my opinion. But of course, you can do all three, and you don't even have to do this as structural. You could still do it as behavioral. I would not recommend data flow. Data flow with this would be a little bit of a mess, especially the adders. All right, so the next step to kind of adding functionality to this ALU is if we want to add subtract to it, what's the kind of new hardware that we would need to implement this? So use the same poll, use the same question, just to change your answer to correspond to this new question. And again, answer this on your own at first, and we'll talk about it together after. Okay, are you guys done thinking about this on your own? Anyone still thinking about this? And we have all changed our answer to the poll to reflect what we think our answer is? Okay, I see you are changing your answers now. Okay, so we're kind of a little bit all over the place in terms of the answers to the poll. So before I send you to talk to each other, I do want to remind you and give you a hint of how are we going to do subtraction in binary 2's complement form. Well, we're just going to add the negative number. Right? Yeah. So with that in mind, how can I use, with minimal hardware change, how can I perform subtraction and talk to the people around you?
Yeah, because you're security. For subtraction.
Okay, just a reminder that when you are done discussing, do change your answer to the poll so I can see how it's moving. Okay, we are moving in the correct direction. So let's talk about this together. So I gave you guys a hint that in order to do subtraction, you're just going to add a negative number instead of actually doing a subtraction, right? So if I want to do A minus B, right? Which one should become negative? B. And then the question now is, how do we make B negative? What are the two things that we need to do?
Inverse and add one.
Invert and add one. So option A, option one, we don't like it because it's inverting A, right? Option two, we like it because it is inverting B. That's the one that we need to convert the sign of, right? And then this XOR is not helping us, right? If we provide an option to use 0 instead of the first carry in, that does not add 1, that adds 0, right? And then if we provide an option to use 1 instead of the first carry in, this is helpful to us because that is how we can add 1. So we need 2 and 5, so we need D. Right? Okay, so now with this in mind, say we make that change, which is shown in the top right, top left here. So now we have B inverts. We have this multiplexer for our input B. If it's 0, we just get B. If it's 1, we get the invert B. And then over here, we have carry. So if we make carry in 1, that's how we can add 1. So then this question, and you don't have to change the poll. Yes, question. You would still have to have 32, right? So we are making A and B 32 bits, but we also have to have 32 of these 1 bit. You could do it where you make A and B 32 bits, and then you model this as 32 bits from the beginning. But we like doing this because then it becomes more modular. Because I can make this now 32 bits, I can make it 16 bits, 8 bits, whatever is needed. Okay, so let's think about this question. So what signals accomplish add? So if I want to add, am I inverting B? No. So I like B invert being 0. And again, I'm not inverting B, so do I need a carry in?
Nope.
Nope. So I like carry in being 0. And then just to check between D and E, operation is 2. So checking 2. That is selecting the output of the adder. So that is add. So we like D. And if we want signals to accomplish OR, do we want to invert B? Nope. And does the carry in matter? So we don't really care what the carry in is, but our operational code should be 1, right? In order to select out of the OR gates. So we like B. And now to do subtract, do we want to invert B? Yes. So B invert should be 1. And then to add 1, what does the carry in need to be? Yep. And then we take the output from the adder, right? So we need 2. So we like C here. So if you're given a new ALU with different controls, different operations, you can, again, look at the function code to figure out what the operation is, right? So if our function code here is all zeros, we should get and, bitwise and out of this. So function at 0, we are not inverting B, right? Because that's what F2 is. And then we have 0, 0. So we're taking this output, which is indeed the and, right? And then we can look at, again, the implementation of subtract for this. So F2 is 1, so we will invert B. So we've got the first part of this working well, and F2 is also used as the carry in for the adder. So that's how we're going to get the +1. So we have inverted, like we flipped the sign of B, which is good. And A is just our other inputs. And now we're selecting from the output 2, which is indeed the output of the adder, right? So if you are given something like this, you should be able to give me something like this. And you should be able to do this, but this is not going, it's not conducive to a 25-minute quiz, right? So I won't ask you to do that way. But you should be able to do it. So are we good with the arithmetic logic units? All right, so we have a little bit of time. We have 8 minutes. So we can begin to look at the next set of slides. And keep this. It's showing up over there, isn't it? Great. Why can I not? Okay, lecture 10. Okay, I need to share. Oh, why is it still? This. All right, it won't let me select. So I want the window, this one. All right, so we are sharing. All right, so first thing that you are making in your lab is a decoder. And I think we only have time to go over this. So the first thing that I want you to do is this. Oh. So this is going, most significant bit is X0. It's not simple for us to implement this decoder if that is the case. What? I'm ready. Okay. X2, X1, X0. Makes it simpler for you because now you can use the equations from the previous slides on decoders. And our decoder, it's fairly simple, right? If the input is binary representation of 0, then the output, the 0th index should be 1, everything else should be 0, right? If it's 1, output is 1, 2, we output a 1 at 2, 3 at 3, 4 at 4, 5 at 5, 6 at 6, 7 at 7. Right? So this is the simplest decoder that you can have. That is still a decoder. I just want to ask you guys a few ideas of how to implement this. So what's one way that you would go about this? Yes. So you can do behavioral. And you can do, so let's write it down. So behavioral case statement. That's one. Right? The case would be on what inputs? Yes, X. And you can output the very simple binary, right? 1, 2, 3, 4, 5, 6, 7, like that. Right? And just do one case for each possible combination of X. And it's going to go into a process block. So what would go on the sensitivity list of this process block? The case statement needs to go into a process block, right? The process block has the thing called the sensitivity list. What needs to go into the sensitivity list for this process block? Yeah, it's X, right? Because what is the sensitivity list for?
All possible inputs.
Not quite. Yes. Yeah, so it just means if any of these things in my sensitivity list change, then I need to reevaluate this process block. So the thing that is important to change here is X, right? And again, just remember that you need default to keep this combinational logic. Otherwise, it will become a latch. And then what's the other way that we can do this? Yeah, we can do data flow, and we have the equations from the slides. So like if we want to simply do, we can do y0 real quick. So it would be y at 0, right? What would this be? When is y0, 1? Yeah, so x at 2, and you need to not it. So here it would be not x at 2 and not x at 1 and not x at 0, right? And then you can do the same for y1, y2, all the way to y7. So you just have 8 equations. And you can do it as this data flow modeling. I would not recommend structural modeling because you don't have a base decoder. We did see that you can make larger decoders with smaller decoders, but you would have to first make the smaller decoder, right? Yes. No, you don't need a clock in this case because we want it to be combinational logic. So the code that I provided for that part, and I told you to copy paste and not really worry about, we will learn how clocks work later on.
Was just so sure.
Both of the digits, yes.
Yeah.
Yeah. Any other question? Okay, so we'll finish going through these slides on Wednesday. And again, do please look at the lab before then.